Okay, this video is on linear programming, and linear programming is a method that is used to optimize a certain function. So we're going to use linear programming to maximize or minimize something. And we have three things involved in every linear programming problem. The first thing is the objective function. Now, the objective function is just an expression that will return the value that we want to optimize. So if you want to maximize volume, for instance, you would have a function that would lead you to the volume of the object that you're looking at. If you wanted to maximize profit, you'd have a function that would tell you, that would give you profit. You'd have an expression that when you put in certain inputs, the output would be profit. If you wanted to minimize costs, you'd have a function, and when you input certain values like number of units or advertising budget or whatever, you would get cost from that expression. So the objective function is just an expression that tells us what the quantity is that we want to optimize. Now, the constraints are another part of a linear programming problem. The constraints are inequalities that place limits on the independent variables of the objective function. So whatever the objective function is, it will depend on some independent variables. Like we were talking about profit before. Profit depends on the number of units that you sell. Or, for instance, volume depends on the dimensions of the object, length, width, and height. So the constraints would put limits on those independent variables, the things that you input into the objective function to get whatever the output is. And when you graph your constraints, in the rectangular coordinate system, the intersection of all your constraint graphs will create what is called a region of feasible solutions. Those are the only solutions that are feasible based on your constraints for the objective function. So these are the three parts that we're going to use to do linear programming. We're going to identify our objective function, our constraints, and then we're going to graph our constraints to find a region of feasible solution. And then when we've graphed this region of feasible solution, we're going to have vertices of that region. We're going to have places where the inequalities intersect each other. Those are going to be called the vertices. And it turns out that the optimal values only occur at those vertices. So we're going to graph this, plug in the ordered pairs that come from the vertices, and the largest one will be the maximum value of the objective function. The smallest one will be the minimum value of the objective function. So let's get started. Here we have a problem. You can pause it and read it if you want, but what we have here is an investor that has $10,000 to invest. He has a choice between a risky investment that pays 20% interest and a conservative investment that will pay 10% interest. So we have different interest rates for each one. The investor wants to have at least twice as much money in the conservative investment than he has in the risky investment. So this person wants to be a little bit more conservative. They want twice as much money in the conservative investment as in the risky investment. He also wants to have at least $3,000 in the risky investment. So he doesn't want to be that conservative. He wants at least $3,000 in the risky investment. So what we're going to do is we're going to find the amounts to put into each of the two accounts that will maximize the interest that we earn. So we're trying to maximize our interest earnings. All right, so the first thing we're going to go try to do is we're going to try to find out what the objective function should be. So let's take a look at the objective function. So try to find, we'll try to find the objective. Now, the objective here, the objective is actually to maximize interest. So I need an expression that is going to give me the interest that this person is going to earn. Well, the interest that this person earns, I'm going to call I. I is a function of the amount of money that I put into the 20% investment and the amount of money that I put into the 10% investment. So I am going to also make variables, these are the independent variables of those two amounts. The first amount, the amount I put into 20% investment, I'm going to call that R. So R represents the amount of money in the risky investment. And the second one, the amount that I put in the conservative investment, I'm going to call C. So I have a function I, which is interest. I is my interest of two variables, the amount of money in the risky and the amount of money in the conservative. So if I tell this function how much money I have in my risky account and how much money I have in my conservative account, it'll tell me how much interest I will earn. Let's come up with this expression for this function. Well, the amount of money, the amount of interest I earn from the conservative investment is going to be 20% of whatever I put into that conservative investment. So the way I write that is I'm going to earn in interest 0.2, which is 20%, times R, which is the amount of money I put in the risky investment. So this term here, this expression 0.2R, tells me how much interest I earn on the risky investment. And I add to that 0.1, which is the interest rate for the conservative investment, 10%, times the amount of money I put into the conservative investment, which is C. So this is my objective function. This objective function, if I give it the amount I put in the risky account and the amount I put in the conservative account, it'll tell me how much interest I earn. So this fits the definition of the objective. The expression that returns the value to be optimized, well, the value to be maximized is the interest. And if I plug in the amount I put in the risky and the amount I put in the conservative, it'll tell me what the interest is. So on the right-hand side, I have the expression that gives me the objective, or the quantity to be optimized. The next thing I want to look at is I want to find the constraints, all right? Well, the constraints are going to place restrictions on my independent variables. The two independent variables here are R, the amount of money in the risky account, and C, the amount of money in the conservative account. So I'm going to look in the reading here to try to figure out what those constraints are. Well, it says here, the investor wants to have at least twice as much money in the conservative investment than he has in the risky investment. So at least twice as money in C as he does in R. So here's what we're going to write for our first constraints. So constraints now. Okay, so the first constraint is saying that the amount of money in the conservative account has to be at least means greater than or equal to, at least twice as much money than is what is in the risky account. So that's how you translate that phrase directly. The investor wants to have at least twice as much money in the conservative investment than he has in the risky investment. So that means the conservative account, the conservative investment, is at least or greater than or equal to twice as much as the risky investment, 2R. All right? So that is one constraint that I have on my independent variables, R and C. Another one, the most obvious one here, is that if I take the amount that I have in C, the conservative account, and I add it to the amount I have in R, the risky account, it has to be less than the total amount of money I have to invest, which is $10,000. So that means that C plus R has to be less than or equal to 10,000. And the last constraint that we have here comes from this. It says he also wants to have at least $3,000 in the risky investment. So he wants to have at least $3,000 in the risky investment. So the amount in the risky investment has to be greater than or equal to at least 3,000. All right, let's see what else we have here. So that takes care of all that. And it says find the amount that must be put into each investment to maximize interest. So we're going to try to maximize the interest. We're going to try to find which one of the vertices from the graphing of the constraint, the region of feasible solution, gives us the maximum interest when we plug it in here. So here are my constraints. The next step is to graph your constraints. Well, I have two variables, C and R. So since I have only two independent variables, I can graph them in a rectangular coordinate system like this one. I just have to choose which one of the axis I want to be the C axis and which one I want to be the R axis. Well, let's see here. Here, this inequality, when I graph it, it seems to me giving me C as a function of R. C is equal, or C is greater than or equal to twice R. So when I graph the boundary line for this region here, for this inequality, it's going to be the boundary line C equals 2R, which implies that I should probably put C on the vertical axis because C is acting like the Y value there. So I'm going to put C on the vertical axis and R on the horizontal axis. So R is like X and C is like Y. All right, let's graph these things. The first one, the first one says that C is greater than or equal to 2R. The boundary line for this first constraint is this boundary line here, C equals 2R. Well, even though this isn't X and Y, I do have here a linear function, C in terms of R. The slope of my linear function would be 2, and the y-intercept would be 0, 0. So let's graph that linear function there. C is equal to 2R. So like I said, my y-intercept would be 0, 0. The intersection of the two um, axis there. And my slope is up 2 over 1. So every time R increases by 1, C will increase by 2. Every time R increases by 1, C increases by 2. So my slope is 2 over 1, rise 2, run 1. And this is the graph of my first boundary line. I just have to figure out where I would have to shade to finish graphing this inequality. So the shading, well, let's see. The shading says that C has to be greater than or equal to 2R, which means that the value of C has to be higher than the values on this line, which implies that I would be shading above the line. If you want to, you can choose test points. For instance, if you choose this test point right here, which would be 1, 4, and plug it into this inequality, 1 for R, 4 for C, you get 4 is greater than or equal to 2 times 1, or 4 is greater than or equal to 2, which is a true statement, which also implies that we would be shading above. All right, let's take a look at the second constraint. For the second constraint, we have C plus R is less than or equal to 10,000. Well, let's go ahead and put this in slope-intercept form, the same way we had this one, by solving it for C, because C is on the vertical axis. So when I solve that thing for C, I will get this. I will get C is equal to, it would actually be in this case less than or equal to 10,000, or R, negative R plus 10,000. I just subtract R from both sides of this equation. So when I solve for C, I get C is equal to negative R plus 10,000. So C equals negative R plus 10,000. And that says that I have, for this equation, a slope of -1 and a y-intercept of 0, 10,000. So for the first equation, the one I drew in red, the slope, remember, was 2, and the y-intercept was the point 0, 0. That's how I got that red line, that red boundary line, and I'm going to shade above that red boundary line. This new one has a slope of -1 and a y-intercept 0, 10,000. So that one, when I graph it, I have to graph it with a -1 slope and a y-intercept of 10,000. So since I have to go all the way up to 10,000, I'm going to let all of these hash marks count for 1,000. So this is 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. So here's the y-intercept of my graph, and the slope is -1. So the slope is -1. So I'm going to go down one and to the right one each time. So from that y-intercept up here, I go down one and to the right one each time. Down one and to the right one each time. Down one and to the right one. Down one and to the right one. All right, so this one looks more like this. Down one and to the right one each time. All right, and for this one, if you take a look here, when we solve this for C, we actually got C is less than or equal to, -r, which means I would be actually shading below this green line. If you want to, you can just choose a test point, like I said before. Choose a test point, like you can choose the test point, let's see, you can choose the same test point, 1, 4, and plug it in. If you plug in 1, 4 into this inequality, you will get 1 plus 4 is less than or equal to 10,000, which is a true statement, which also tells me would be shading below the green line. Lastly, now I need to graph this last one here. I can't solve this one for C. If you have a linear equation and you can't solve it for the vertical axis, the dependent variable, it means you have a vertical line. So this is a vertical line where r is equal to 3,000. So I'm going to graph this one. The boundary line is r equals 3,000, which has an undefined slope and an x-intercept of 3,000, 0. So since I'm going by 1,000, this is 1,000, 2,000, 3,000, and I get this vertical line here, this blue vertical line. Okay, and now I can look at my region of feasible solution. I'm going to color my region of feasible solution in purple, all right? So here's what I need to be. I need to be below the green line, above the red line, and since r is greater than or equal to 3,000, I need to be to the right of the blue line. So below the green, above the red, and to the right of the blue is this region right in here. Very small region. This is my region of feasible solutions. This is my region of feasible solution. All right, when you have your region of feasible solution, the next step, my region of feasible solution is in purple. The next thing you want to do is you want to find the vertices. You want to find where the lines that create your region of feasible solution intersect each other. So let's look at the vertices of my region. There's this vertice right here in black. There's this vertice right here in black. And there's this vertice over here in black. So we need to find the intersections of these three. We need to find these 3 points right here, those ordered pairs. So what we're going to do is we're going to come to the equations over here and try to figure out where they cross each other. Well, the blue line is easy because the blue line, all the values of r are 3,000. So this point, for instance, has a value of r that is 3,000 because it's on the blue line. And if you know that r is equal to 3,000, you can figure out where you are on the red line. If R is equal to 3,000, you plug 3,000 in here, you get C is equal to 2 times 3,000, 6,000. So the intersection of the blue line and the red line is the point where X is equal to 3,000, or sorry, R is equal to 3,000 and C is equal to 2,000. So that ordered pair would be the ordered pair 3,000 for R and 6,000 for C. That's one of the vertices of my region. The other one, R is also equal to 3,000 at this point right here. So R is 3,000, is on the blue line. So R is 3,000. And if I plug that in here, I get C is equal to negative 3,000 plus 10,000, which is 7,000. So this point up here, this top vertice up here, let me actually just erase this part here because we actually don't need that. We already have our region. All right, so this top vertice right here has the ordered pair where this our value of R is still 3,000, but now the value of C is negative 3,000 plus 10,000, which is 7,000. 7,000. All right, the last one I need to find is this intersection right here, the intersection of the green with the red. The intersection of the green and the red. So the intersection of the green and the red. That's these two inequalities right here. Green and red. All right, so we need to know where these two equations intersect. So let's use the method called substitution. Since I already know that C is equal to 2R, I can plug that in here and get that C, which is 2R, is equal to negative R plus 10,000. Negative R plus 10,000. And I can use this to solve for R. I just add R to both sides to get rid of this negative R. I get 3R is equal to 10,000. And I divide both sides by 3. So I get R is equal to 10,000 over 3. And a third of 10,000 is what we have for the value of R. And then once we know the value of R, we can use that to find the value of C for this ordered pair right here. We already know that R is 10,000 over 3. And 10,000 over 3 is $3,333.33. So that the first point here, R, the first coordinate is 3,333, $3,333.33. Now, when we plug that value in to this equation to find C, we find C is equal to 2 times R, which we just found out was 10,000 over 3. So we get that C is 20,000 over 3. A third of 20,000. 20,000 over 3 is the value of C at that point. And 20,000 over 3 is $6,666.67. That's $6,666.67. So there I have all the vertices of my region of feasible solution. Once you have all the vertices of your region of feasible solution, the next step is to take those vertices and plug them in to the objective function. The largest value will be your the largest value will be your maximum. The smallest value will be your minimum. So let's go ahead and do that now. All right. So Let's go ahead and grab our objective. This is the objective function. Can't forget about that. Here's the objective function. And what I'm going to do is I am going to plug all those ordered pairs that we just found for the vertices of our region of feasible solution. I'm going to plug all those ordered pairs in to this function and see which one gives us the maximum value, because the maximum value has to occur at one of those vertices. So let's see what these numbers are. We have 3,000, 7,000 for R and C respectively. So I need to find the I of 3,000, 7,000. So this would be as if I put $3,000 into the risky account and $7,000 into the conservative. This is going to be zero point 0.2 times 3,000 plus 0.1 times 7,000. Let's see what this gives us. This gives us 0.2 times 3,000 is 600. And 0.1 times 7,000 is 700. So at the end, if I put $3,000 into the risky and $7,000 into conservative, I will make, what's this, $1,300. All right, now I need to try the other ones. Let's see. Well, since I'm looking for a maximum value, it doesn't make any sense to put in 3,000, 6,000. That just doesn't make sense because that's not even investing the entire $10,000. That's just investing 9,000. So this one probably won't give us the maximum. So let's try this one. Let's try this one. So this is going to be 10,000 over 3 and 20,000 over 3 that we're plugging in. So it's going to be 10,000 over 3 in the risky. And I'm using the fractions because I find it easier to do the calculations when I'm not using a calculator. 10,000 over 3 and 20,000 over 3. But you can also use the decimal approximations that I gave. 20,000 over 3. So we get here zero point 0.2 times 10,000 over 3. And we get 0.1 times 20,000 over 3. And let's see what this yields for us. All right, this is going to yield, let's see, zero point 0.2 times 10,000 is 2,000. I mean, not 2,000, sorry. 0 point 0.2, well, 2 times 10,000, 20,000. Yeah, 2,000 over 3 plus 0.1 times 2,000 or 20,000 is also 2,000 over 3. So I get here, this is going to be 4,000 over 3. And 4,000 over 3 is going to be 1,000. Let's see, that's 3 goes into 4, that's once. And then we have a remainder of 1/3. So 1/3 is going to make this a bunch of 3's repeating, right? 3.33. So if I invest 3,000 into the conservative or into the risky and 7,000 into the conservative, I'll make $1,300 in interest. But if I invest this number, which was $3,333.33 into the risky and $6,666.67 into the conservative, I'll actually make $1,333.33, which is 3,000 or $333 more than I would make if I did this. So it turns out that the maximum interest that I'm going to make comes from investing into the risky $3,333.33, which is the 10,000 over 3, and into the conservative $6,666.67, which is the 20,000 over 3. Uh, this should be a 3. Okay, so this is how linear programming works. It's a bit tedious, but not impossible to do. And that is it.